Swayam Prabha. Digital India. Educated India.
In this model, we are going to discuss cross movements. In the earlier models, we have started with the basics of probability, then we have discussed the single dimension random variable. Then in the third model, we discussed the moments and inequalities for a single dimension random variable. Then in the fourth model, we discussed the standard distributions, both the discrete and the continuous type. And in the fifth model, we discussed the 2 and higher dimensional random variables or random vectors. In that, we discussed the joint probability mass function, joint probability density function. In the same model, we discussed the independent random variables also. In the sixth model, we discussed the functions of several random variables. In that, we discussed the distribution of functions of several random variables, and we discussed order statistics. Then we discussed conditional distributions and random sum. In this model, we are going to discuss cross movements. In this section, we are going to discuss cross movements with the following lectures. The first lecture, we are going to discuss various movements. The first order movement, second order movement, and so on. Then we are going to discuss covariance, variance matrix. That is in the first lecture. In the second lecture, we are going to discuss correlation coefficient and linear regression. In the third lecture, we are going to discuss conditional expectation. Let us start with the moments. Before going into the moments of first order, second order, and cross movements for multidimensional random variables, first let me give the definition of expected value of a function of a random vector. That is a definition. So this definition is going to be useful to compute the various moments of the several random variables. Let x1, x2 and so on, xn be a n-dimensional random variables, and let G be a real valued function defined on Rn. That means it has a n variables. The expected value of the function g of x1, x2 and so on xn, that is denoted by expectation of g of x1, x2 and so on x of n, that is defined as expectation of g of x1, x2 and so on xn, that is equal to, suppose x1, x2, xn are discrete type random variables, then this is going to be summation n summations with respect to x1 and the second summation is with respect to x2 and so on, the last summation with respect to xn of g of x1 and so on xn. The probability of x1 takes a value 1, x2 takes a value x2 and so on, xn takes a value xn, when all these random variables are of the discrete type. If all such n random variables are of the continuous type, then it is a integration from minus infinity to infinity and so on. It is a n dimensional integration with the integrand g of x1 and so on xn multiplied by the joint probability density function of x1, x2 and so on with the variable x1, x2, xn. Integration is with respect to x1, x2 and so on xn, when all these random variables are of the continuous type. Provided when the random variables are of the discrete type random variable, the summation in absolute sense it is finite, or when the random variables are of the continuous type, in absolute sense the integration has to be finite quantity. That means the provided the right hand side is finite in absolute sense. This is the same thing we have done it for only one dimensional random variable. When x is a random variable, g is a Borel measurable function, g of x is a random variable, one can compute the, or one can find the value, that is expectation of g of x with the summation if it is a discrete type random variable, integration if it is a continuous type random variable, provided the summation or integration is going to be a finite quantity in absolute sense. The same provided condition is extended with the n dimensional random variable, and we are finding the expected value of the function of random variables, that is g. When we say g is a real valued function, we assume that this is going to be a Borel measurable function. In that we are finding the expectation of g of x1, x2, xn. Again, we are not finding the distribution of g of x1, x2, xn. We are directly computing the expected value of the random variable g of x1, x2, xn. To find the various moments, you can use this definition nicely so that you can get the various moments. Before we go to the various moments, let us give a one simple example of how to compute expected value of the function g of x1, x2, xn. That's a simple example. Example 1. Let x comma y comma z be a three-dimensional continuous type random variables with joint probability density function is given by joint probability density function of x, y, z that takes a value a times x, y, z when x takes a value 0 to 1, y takes a value 0 to 1 and z takes a value 0 to 1. It's not 0, a times x, y, z in these intervals, 0 otherwise. We can verify whether this is going to be a joint probability density function by integration from 0 to 1, 0 to 1, 0 to 1, a times 8xyz dx dy dz, that is going to be 1. Therefore, this is a joint probability density function of the random variable x, y, z. The question is, find expectation of 5x minus 2y plus z. Find expectation of 5x minus 2y plus z. You can apply the previous definition. So here the g of x1 comma x2 x3, that is same as 5x minus 2y plus z. Since all are of the continuous type random variable, make the 3 integration minus infinity to infinity, minus infinity to infinity, minus infinity to infinity, that is 5x minus 2y plus z times 8xyz dx dy dz, that is going to be the expected value. That is expectation of 5x minus 2y plus z, that is same as, since x, y, z lies between 0 to 1, it is 0 to 1, 0 to 1, 0 to 1, 5x minus 2y plus z times 8xyz dx dy dz. You can do the integration and you can get the value. That value is 8 divided by 3. Fine. So this is a very simple example in which we are finding the expectation of function of random vector. Now we will move into the next definition. We start with the two-dimensional random variable. Let x comma y be a two-dimensional random variables if the expectation of x minus expectation of x the whole power I multiplied by y minus expectation of y the whole power j, if this expectation exists, that means in absolute sense this expectation value is going to be a finite. For non-negative integers I and j, we say that this value is a central moment of order I comma j for the random variable x comma y, and it is written as, it is denoted by mu suffix I comma j, that is expectation of x minus expectation of x the whole power I, y minus expectation of y whole power j. After the expectation of this function of x and y exist, we can conclude this value is going to be the central moment of order I comma j for the random variable x comma y, that is denoted by mu I comma j. Here I comma j both are non-negative integers. This is a special case of the definition which we have given the expected value of a function of a random vector, because this is a very special function, that is one is x minus expectation of x power I multiplied by y minus expectation of y power j. We can have a few results over this definition, or remarks, or some results. The first result is if you substitute I is equal to 1 and j is equal to 0, or you substitute I is equal to 0 and j is equal to 1 in the definition. Either you substitute I is equal to 0, j is equal to 1, or I is equal to 1, j is equal to 0. In both the situation, you will get the value is going to be 0. Second result, suppose you put the value I is equal to 2 and j is equal to 0, that is nothing but expectation of x minus expectation of x the whole power 2. And this is nothing but variance of the random variable x. Similarly, if you do mu of 0 comma 2, that is same as expectation of y minus expectation of y power 2, that is same as variance of y. When you substitute I is equal to some integer, positive integer, and j is equal to some other positive integer, then you will get the central moment of order I comma j for the random variables x and y, or the random vector x comma y. As a special case, there is the next result. When I is equal to 1 and j is equal to 1, that is nothing but expectation of x minus expectation of x multiplied by y minus expectation of y, which has the special name. So, that I am going to make it as the next definition. That is definition that is called a covariance between x and y. Let x and y be a random variables defined on the same probability space such that the second order moment for the random variable x exists and the second order moment for the random variable y also exists. Then we can define the covariance between x and the random variable y, that is defined as the notation is COV x comma y, that is same as that is mu of 1 comma 1, that is a expectation x minus expectation of x multiplied by y minus expectation of y, where expectation of x is the mean of a random variable x, expectation of y is the mean of a random variable y. First you multiply x minus expectation of x with the y minus expectation of y, then you find the expectation. So this is a special case of the first definition which we have given, expected value of function of random vector. The previous definition, it is I is equal to 1 and j is equal to 1, which has a special name that is called the covariance between these two random variables. This has the few important results that I make it as the points one by one. Either you can compute expectation of x into expectation of x multiplied by y minus expectation of y, or if you do the expansion, if you expand this, that is x into y, x into expectation of y, similarly expectation of x into y, then expectation of x into expectation of y, that is same as covariance of any two random variable is same as expectation of x into y minus expectation of x into expectation of y. The second result, if you find out the covariance of x comma y, which is same as covariance of y comma x, that means by interchanging the role of x and y, you will get the same value, that is provided it exists, the covariance of x comma y, which is same as covariance of y comma x. Third result, suppose I compute covariance of x with x itself. You substitute, you replace y by x in the above definition. That means it becomes expectation of x minus expectation of x, again x minus expectation of x, that is same as expectation of x minus expectation of x the whole square, that is same as variance of x. The fourth property, that is the covariance of ax plus b with the other random variable y, that is same as if you expand by using the definition of covariance, you will get a times covariance of x comma y and covariance of b with y, that is going to be 0. Covariance of any constant with one random variable, that is going to be 0. Therefore, covariance of ax plus b when a and b are constant, covariance of ax plus b with y, when a and b are constant, that is same as a times covariance of x comma y. The next result, result number 5. Suppose the random variable x and y are independent. Suppose the random variable x and y are independent. We know that the joint CDF is same as the product of two CDFs. If they are discrete type random variable, then joint probability mass function is same as the product of probability mass functions. If they are continuous type random variable, then the joint probability density function is same as product of probability density functions of x and y. So here we are computing the covariance of x comma y, that is same as expectation of x into y minus expectation of x into expectation of y. When two random variables are independent, if you compute the expectation of x into y, that is same as, suppose I assume that both the random variables are of the continuous type, that is nothing but minus infinity to infinity minus infinity to infinity x times y, the joint probability density function of x comma y dx dy. I am making the assumption both the random variables are of the continuous type. Similar derivation I can do it for discrete type random variable also. Since these two random variables are independent, I can use this condition, that is this is in the CDF, and I can use the condition in the joint probability density function. Therefore, this is going to be minus infinity to infinity minus infinity to infinity x times y, the marginal distribution or probability density function of x and y. Now, the same double integration can be written as minus infinity to infinity x times f of x dx multiplied by minus infinity to infinity y times probability density function of y with respect to y. This is because of the joint probability density function can be written as the product of probability density functions of x and y. Therefore, I can keep x, f of x together, similarly y and f of y together. Therefore, the integration becomes product of these two. We know that the first integration is expectation of x and the second integration is expectation of y. That means we have given the derivation for considering both the random variables are of the continuous type. Even if you do both the random variables are of the discrete type, you will get the same conclusion, that is expectation of x into y, that is same as expectation of x into expectation of y. Therefore, if two random variables are independent, then the covariance between the random variables x and y, that is same as expectation of x y minus expectation of x into expectation of y. But just now we got the result, expectation of x y is same as expectation of x into expectation of y. Therefore, the covariance becomes 0. This is the fifth result. That means if two random variables are independent, the covariance is going to be 0. Converse, that is if the covariance is covariance of two random variables x comma y 0, that does not imply two random variables are independent. That means converse is not the covariance that is covariance between any two random variable 0, that does not imply the random variable x and y are independent random variables, does not imply, whereas x and y are independent random variables, then covariance of random variable x comma y, that is going to be 0.